All right, hello everybody. So this week we'll be reviewing the first part of topic 4. And so kind of be doing a little bit of linear expressions. We'll get to combining like terms. How do you analyze if something is equivalent or not? So let's jump in right away. First, I want to just do some terminology review because I'm going to be referring to these over the video and they're just things you should know. So constant, coefficient, variable kind of make up our linear expression. So let's take just a random one. I'll make up one off the top of my head. Let's take something like 8x plus 3. So a very typical linear expression, one you might see a lot. So we've got, of course, the easiest one. We've got the thing that variable. So that's our variable term. And so could be x, could be y, could be any symbol you want. We could even put like a dinosaur symbol there. It could be 8 dinosaur plus 3. But here we're going to use something that's very mathematically common. We'll use an x. Next, we got the term that's attached to our variable, or what's multiplying by the variable. We call that our coefficient. And not just limited to linear expressions. Even if we had something that was like a non-linear expression, if we had something like 8x squared plus 3, that would still be our coefficient right there. But let's erase that for now because we don't want to worry about a nonlinear quite yet. And then finally, we got kind of that term that's being tacked on with either an addition or a subtraction symbol, and that is our constant. Why we call it a constant is because no matter what x is, x could be 100, x could be 1,000, x could be 100 million. This 3 is just hanging out along for the ride, and at the end of the day, it'll be added on. So that's our constant. We sometimes call it our starting value. Oop, let's fix that. And then other thing is, why do we call it an expression and not an equation? Well, it's not an equation because there's no equal sign. All right, so let's go ahead and move on. Let's jump into some couple examples. First, we'll start with writing these expressions. So we're going to look at an example that we looked at earlier in the year to review. So I'll read it off. We'll kind of analyze it together. So first off, we got an automatic dog feeder. So here's our dog feeder right there. If you've never seen these before, basically what they do is you can put a setting in. So you fill up this reservoir, and then if you put a setting, you can say, oh, I want it to spit out a certain amount of dog food per day. So this one's set to spit out 2/5 cups each day. So at a certain time interval, maybe in the morning, maybe at night, it'll spit out automatically a certain amount of dog food. Or you can do it twice per day. Maybe it's 1/5 cup twice per day. But either way, we got 2/5 cups each day. So now we're going to try to write an expression that I can figure out how much food to feed my dog Charlie. See how many days it'll last. So essentially, we've got a reservoir, and we got to figure out how much food will be left in this reservoir after an unknown variable amount of days. So first, I like to always ground these in kind of a visual. So we'll start with a bar diagram. So let's assume that when I fill this up, I fill it up to the brim. So let's assume that I fill this up to its capacity. So I'm going to start by assuming that. So I'm going to say my starting or my coefficient value is going to be the entirety, the 20 cups. And so I'll have my visual, I'll have my expression. It's going to start with 20. And now we're just going to analyze, well, what happens each day. So I'm not going to worry about the variable yet. Let's just worry about what happens if I just spend 1 day away from Charlotte. So I go on a 1-day vacation. So if I go 1 day, we're not going to add to this value that's in here. It's going to be spitting out. So it's going to spit out 2/5 of a cup. So negative 2/5 times 1. Next, well, what if it goes 2 days? Well, that's just 2 jumps of negative 2/5. So that'd be 2. So let's extrapolate it out a little further. What if I had an unknown number of days? Or d days? Well, I would take d and I would multiply it the number of days by the amount of dog food that gets dispensed per day. So essentially what that leaves me with is negative 2/5 times d. So I could write this in two ways. I got my 20, my starter, and I could add a negative 2/5 times however many days. But of course I could just rewrite this as subtraction. So plus a negative 2/5, that's just 20 minus 2/5 times d. So excellent. So let's try answering a question with this now. So let's answer the question, how much food would be left for Charlie if I left for 10 days? Say I left for 10 days. So we can use this expression here and we could figure that out. So I've already set, and actually I'm going to go back because I made a big mathematical mistake. I made an expression, but I didn't define what my variable is. So let's set d is equal to, or is defined as, the number of days. So maybe even more specific, let's say since filling. And if I look at this expression here, well, I've got a value for that variable now. So d is no longer unknown. D is going to be equal to 10. So I can just plug this in now. So if d is equal to 10, I can just substitute it back in and figure out what this expression equals. So what I'm going to do here is I'm just going to take my expression, 20 minus 2/5, but I'm not going to write d here because I know what d is. It's 20, or excuse me, it's 10. So I get 20 minus 2/5 times 10. I can evaluate that out. And if I want to, I can do this even without a calculator. So minus 2/5. 10, of course, is the exact same thing as 10 over 1. And I can just reduce this down. 10 divided by 5 is just 2 over 1, just cross cancel. And I get, that's 20 minus 4. And I have 16 cups left. Excellent. All right, so now we've got kind of how to write these. Let's go over quickly what happens if I have an expression that might look very similar, or excuse me, but might look very different, but is secretly very similar. So we're going to look at this example we looked at earlier in the year. So this is the dance concert. So we've got 3 student council members, and they each made an expression. So the situation is they've got these tickets. The tickets sell for $6 each, but they already spent $300 on the supplies. And each of the members, we can think of member 1, member 2, member 3, they each come up with an expression that they think represents it. So just to refer back to, I'm going to give these people some names. We'll give them some silly names. We'll call this Goro. We'll call this student council member, we'll call them Captain Bob. And finally, we'll give this member about the name Jim. Why not? All right, so let's start with what's probably the most simplistic expression. So this one, probably the most simplistic expression. So here we've got 6t minus 300, and we'll give that person's title. So we can see here that this is kind of like the expression we just made for the dog food, which we've got 6 times t, where t must be then number of tickets sold. They define that in our paragraph here, but let's just define it over here anyways. So 6 times the amount of tickets minus that 300 that they already spent, that should give how much they raised. So I think we can pretty definitively say Goro's correct. However, the other 2 members' expressions are a little bit different looking, so I don't know if we can definitively say as much, but we shall see. All right, minus 300 plus 6t. So let's try something really quick. So what if I just plug in a random value here and see what I get? So let's just assume, or let's analyze the situation. What if they sell 100 tickets? So we'll set our variable for 100. We'll see what happens. So let's plug it into Goro's expression first. So we get 6 times 100. I'm just going to replace the t with a 100. And I get 600 minus 300, which gives me 300, which says they raised $300. All right, let's try with council member number 2. So here I can plug in 100 for my variable t. I get 100 minus 50 times that whole quantity times 6, which gives me 6 times 50, which then again gives me 300. These expressions look very different. They yield the same thing. So let's move on to council member 3, see what they yield. So minus 300 plus 6 times 100, and I get minus 300 plus 600. 6 times 100 is 600. Negative 300 plus 600. That will again yield us 300, which says that, at least for this value of 100, we don't know for all values yet, but at least for 100 tickets, they all told me that this dance raised the same amount of money. So I want to try something else now. So perhaps these expressions are more similar than we think. So I'm going to take Goro's. Goro's is already in standard form, so we don't really need to do anything with that. So we've got our first expression. Let's look at expression number 2. So I've got 6 times the quantity t minus 50. And if I look at this, well, it's stuck in this form, but I could also use my distributive property to expand this out. So let's try this. So 6 times t, and of course gives us 6t. 6 times 50, and of course positive times a negative is a negative. That gives me 300. So what I've done here, shown these expressions are the same. So not only did they work for one specific variable, outputted the same thing, they should work in every single case because I rearranged it and they're the same expression. And let's finally do the same thing with council member 3. So I got minus 300 plus 6t. And of course I can just rearrange this. So this is addition. I could put this out front. It doesn't matter if I add on my profit at the end before taking into account my losses. I can just take the 6t, rearrange it to the front. So 6t, and I can think of this as like plus a negative 300 if you'd like. And you can see, well, plus a negative, that's the same thing as just writing that as subtraction. And we've got council member 1 had the same expression as council member 2 as council member 3. So you might be given some expressions, or you might generate some expressions that look wildly different, but through just some careful manipulation, kind of knowing what you're doing, you can really find that they yield the exact same thing. All right, let's look at one more example. So not only are you going to want to find equivalent expressions, but sometimes you just want to whittle down an expression to something simpler. So we're going to take a look at kind of that concept of combining like terms. So we're going to start with the visual, and then we'll kind of connect it to the algebraic. So let's start with this example. So we're not going to worry about the algebra yet, so I'm just going to go ahead and cover that up. We're going to worry about the visual. So it looks like we've got a variable of c. Let's call that our variable. So looks like C tiles, C tiles, C tiles. And it looks like we got some constants here. So terms that aren't attached to variables at all. So as you can see from the visual, this is almost like a 1 by C block. And if we don't know what C is, so this is the visual. C could be, as long as it's shown on the screen, could extend all the way down to the center of the earth. We don't know. So this is just, we're visualizing it for the meantime. So, but what we can readily see is we can't cancel out a C with a constant. They're different types of terms. But what I can do is I could cancel out or combine C's with other C's. So let's look for pairs that we can cancel out. So for instance, I have a C and a negative C. Those should undo each other. So we'll take 2 pieces off the board. And I can keep doing that. So these two negative C's cancel out with these 2 positive C's. Let's cancel out one more pair. And I'll do the same thing with the constant. So -1 cancels out with 1. And I'll keep going. And of course, we got 5 from both the positives and the negatives to cancel out. So now let's look at what we're left with. So I'm left with 3 negative C's, which could also be just written as -3C. And I'm left with 2 positives. So visually, this whole thing is equal to -3C plus 2, because we can just whittle it down. So now let's look at this algebraically. So I'm going to go ahead and clear my space real quick. Look at it algebraically. So if I have all these out on a table here, it's kind of like I'm combining them. I'm combining them into one pile, which is the same thing as just adding all these terms together. Now let's look at each part separately. So here, this is like -2C's. I got 3 positive C's. I've got -5 here. I've got 1, 2, 3, 4, -4C. And I've got 7 here. And I'm kind of combining them all up. So I'll bring those pluses that I've written down here up here, which really can just be written into this expression here. So let's look at this algebraically. I'm going to copy it down first, and I'm going to kind of color code it. So all the C's will write in one color. Give 2C plus 3C, and then let's maybe do these in purple. -5 plus a 7 out here at the end, and of course, let's not forget -4C. So what I'm going to do here is just like I canceled the tiles out visually, I'm just going to do it algebraically. So no pictures, just using the algebra here. So anything that has a variable term in it, it's got to have the same variable as well, because if I had a different variable, it could obviously be a very different length, so we couldn't combine them. So let's group up all the terms that are alike. So -2C plus 3C minus 4C. Just rearranged it, bringing the negative signs with it. If it helps, I can think of this as a plus -4C, which makes it just rearrangeable with that there. And then I've got my constant term, so my -5 plus my 7. And now I just combine them. So I could start, this is just like integer operations. So -2 plus 3, I'm just dealing with their quantities of C. That leaves me just with 1C, which is the exact operation I did up here when I did, oh, well, that cancels out that cancels out that, and I'm just left with 1C left over. I combine the like terms. Let's bring over everything else down that we have. -4C, -5, plus 7. And now let's combine the rest. So 1C minus 4C, that's the same thing as the operation 1 minus 4 with the C along for the ride. So 1 minus 4 is -3. And of course, these are C terms, so let's pop it down here. And that was the exact same thing I did when I canceled out this positive 1C with this negative C, and I had -3C left over. And now we just do the same thing as the constants. Well, -5 plus 7, that's an operation I can do. I can just evaluate that. -5 plus 7, that's of course plus 2. And that's the exact same thing as canceling out 5 negatives with 5's positives over here. Just be left with plus 2. So again, just to kind of recap, we had an example of writing expressions. We had an example of how do you look at expressions to see if they're equivalent or not. And we had this example of how to combine like terms. So we'll kind of split up this review into 2 weeks, since this is such a crucial unit, and also one that I think a lot more stuff to go back on. So I'll post some review on this. Again, if you have any questions, please bring those questions to our Wednesday office hours. So I hope this was helpful, and hope you have an excellent week.